Okay, grade 11, this is lesson number 7, Standard Deviation and Error Bars. Now hopefully you guys have been on Schoology and you've seen that I've updated some of our due dates, so you were asking about final due dates for stuff in this unit. So we're not doing a test. I put the date for your statistics assignment. It'll be open book but done on Schoology so I can see you guys doing it. Just doing a few different statistical tests. And then a week after that, May 27th is the day your mock IA is due. And then June 4th till June 8th will be time for whatever finals situation is having. It's still being debated. We don't have a decision yet for whatever the finals are going to be. So we're moving on now and talking more about stats and less about design, because we have all our design lessons are already done. Okay, so let's talk about linear and non-linear relationships to start off with. So last class, you guys learned about different kinds of relationships that variables can have. Can you remember the different kinds of relationships? So we have linear, non-linear, and of course, positive and negative correlations, as well as strong and weak correlations. Those were two types that we talked about last class. We can also talk about them as being linear and nonlinear. So take a scrap paper, and here's a linear scatter plot. You see the overall trend here looks linear. We can also draw nonlinear ones. Okay, so take a minute and try and think what some nonlinear relationships might look like, and then draw them. Okay, so if you look here, nonlinear, first one we have here is a nice curve, kind of half a parabola kind of shape. And the second one here, nonlinear, is going up and going to go down. So what kind of situations, what kind of relationship might cause that particular shape of graph to turn up? Think about that for a second. So a good example of nonlinear could be a variable that's going to be increasing to a certain point and then kind of slowing its increase. An example might be, for example, if you have a bakery and a baker, the amount of loaves of bread output is increasing as they hire more bakers up to a certain point. And then it's going to increase, it's going to decrease, they hire too many bakers, so everyone's getting in each other's way. So that could be an example of this relationship here. You could also talk about, you're going to start off the slow growth and then increase. Lots of different relationships besides just linear relationships. So if your data shows up as being something besides linear, that doesn't mean there's no relationship. Okay, so here's some more examples. So here we have a nonlinear kind of relationship here, showing the HDI, the Human Development Index, and the number of cell phones. Okay, and of course, in case you don't already know, HDI is a combination of economic information, life expectancy, education, as general measure of quality of life, is the mean of that particular statistic. And then over here, we have a graph we've seen before with the amount of salt in the soil decreasing, but then no longer decreasing anymore from the bacteria in the soil, because it can only decrease it so much, and it kind of plateaus. Okay, let's talk about proportional relationships. So we have talk about that they're proportional if they're direct or inversely proportional. It's another good way to talk about how your variables are related to each other. So in a direct proportional relationship, as one variable is increasing, the other is decreasing. Is also increasing. So as this variable is going up, this was also going up, so we have this very clear linear relationship here. A great example is earnings and hours worked if you work in a paid by the hour type of job. For salary jobs, it doesn't really work. If it's inverse, then as one increases, the other decreases by the same amount. The key factor here is the same amount. In these two examples, we have 0.5 as a factor here, and 600 is a factor here. Okay, so example of an inverse, as your speed increases, your travel time will decrease. Okay, so let's talk about the normal distribution. A lot of data follows the normal distribution, and a lot of time we can compare all our different sets of data in our sample with the normal distribution. And this is a way to help you kind of see if you're finding data that follows a trend, a normal kind of distributed trend. So when you plot your data, it can be distributed into several different forms, and the normal distribution is a very common one. That's why it's called the normal distribution. And what it means is the center point here, the 0 value, that's the mean of your data. So most data is close to the mean. So if you think of kind of like a histogram where this is the most points are going to be the most values are going to be close to that mean. And then as you get further from the mean on both sides, the number of points of those values decreases. So in examples of this, people's height follows normal distribution, blood pressure follows normal distribution, a lot of things with biology follows it. Things that have kind of a normal level of variation will be following the normal distribution. But not everything does. So sometimes you can get things that have an asymmetrical distribution. Now, how can you know this without just graphing and making a histogram? A good way to know it is just look back at your mean and median mode. If the mode, median, and mean are very similar, if not exactly the same, then you're going to be having a symmetrical distribution and something like the normal distribution. However, if they are quite separate from each other, like we have a mode over here, the most common, my mean is over here, my median's up here. This means it's going to be asymmetrical. There's something different in the distribution. And if they're quite different, that should mean you need to look into this more because maybe it means some of the statistical tests that assume you have a normally distributed data set will not work. A lot of the time, this is why you have to collect a certain minimum number of data points to make sure you have enough data points to get it to hit the normal distribution. Okay, so let's look at some examples here from all the IB exams. So here's a graph with mean results for two genetically modified varieties used in trials, and control results are shown in the bar below. So we have different soils and we have different types of varieties of something. I think it's corn. So the control and the two genetically modified ones. Okay, and then it says, first question, the mean mass of flagellates in GNA2 number 28. So flagellates is the black one. That's this GNA2 28, this one. So the black bar here was 63% lower than the control. So here's my control, and there's that one. The mean mass of amoeba in GNA2 number 28, so same trial here, amoebas are white here, was 51% lower than the control. So again, here's my control, here's my amoeba. Calculate how much lower the mean mass of nematodes, here nematodes are the gray ones, in the GNA2 number 28 trial was than the control. Show your working. So this is a calculation we have to do in IB exam paper 2 or paper 3. So we need to be able to read the numbers off the data table, and they gave you the two examples here with the first two that are worked out to kind of help you, but to go back and kind of work backwards from how they figured that out, that's going to take a lot of time on an exam. So it's best that you know how to do this and you have that kind of intuitive math knowledge. I'm not going to spend, I'll go over it, but I'm not going to spend a lot of time on this. But if you do need help with this kind of stuff, then please make sure you get some help, okay? So here's examples of the answer key. So you'd have to do percentage, the percent difference is mean mass of the control minus the mean mass of a GNA 28. So to read those numbers off the graph, divided by the control. So what's the difference divided by the control times 100%? So they read this off the graph here as 5,500 for the control, and the nematodes in GNA number 28 is 3,700 divided by 5,500 times 100%. Now you notice that plus minus 50, that means they're going to take, if you do this, but let's say you said 5,450 or 5,550, you'd still get the points. So giving some generosity because it's not really easy to read that graph. Or you can also show this, 1 minus the mean mass of the G number 2 over mean mass of the control, or the calculation like this. And your final answer, second point, which should be 32%, but they'll give you plus or minus 2.5%. So 34.5% is okay, or 29.5% is also okay. Okay, so let's talk about standard deviation. So standard deviation is how far spread out the numbers are from the mean. So in a traditional normal distribution, 68% of values are within one standard deviation, one standard deviation below, one standard deviation above the mean. While 95% here are two standards below or two standards above. They add all those numbers up, we get 95%. 99.7% are within three standard deviations of the mean. So we have very few 0.3% are within more than three standard deviations of the mean. Now, what the standard deviation is differs for each data, so you have to calculate it. You can do this with Excel, with a calculator. A lot of people have a button for it, but we're going to learn how to do it by hand, just so you really understand what it actually means. And the standard deviation can tell us a lot about the data, about how variable it is, about what it means, that kind of stuff. So here's a little video we're going to work through to kind of see how you do this calculation. So let's go ahead and have your data set here. You're going to take the mean of your data set. Okay, so you have to have a data calculator. And we're making up a little data set here to practice with, adding them up, calculating the mean of that data set. Okay, so we've got the mean of our data set. Thank you, we know how means work. And then you're going to take each data point and subtract the mean from it, and then square that. Okay, so I take the data point minus the mean I just calculated, and then square that value, end up with a positive value. And then I add up all those standard deviations and take the mean of those. And then the square root of the mean of the standard deviations of the squares, and that's standard deviation. In that case, it was 6. So we'll look through an example step by step as well here. So here we go. Here's your values in the sample. Okay. Take the mean of those samples, and the mean is 5. And then you're going to figure out the difference from the mean for each data point. So the first data point is 2, so I take 2 minus my mean of 5, I square it, so minus 3 squared is 9. Then my next data point is 4, so I take 4 minus 5, which is the mean, square it, minus 1 squared is 1. I have 3 4s, so that's 3 times. And I have 5 minus 5 is 0, squared is still 0, and I have 2 5s, so I do that twice. I have 1 7, 7 minus 5 is 2, squared is 4, and then 9. 9 minus 5 is 4, squared is 16. I'm going to take all of these points, which is the difference from the mean, and I'm going to add them up, divide by the total of them, which is 8. So I take the mean of those points, and then take the square root of that, and that gives me a total value of 2. So 2 is a standard deviation for this data set. The standard deviation is 2, which is a pretty low number, which makes sense because this data set is pretty small range. A lot of points are very similar to each other. So here's another formula version you're looking at. Sometimes I'll give you formulas like this, but if you don't know how to read them, it's not very helpful. So X little bar on top is always the mean, so figure out the mean. Okay, then I take each data point, xi is a single data point, minus the mean squared, with the sum of them, so for every single data point I do that. Take the n, the number of data points, minus 1, divide by that, and take the square root. Same things we previously saw, just another way of looking at it. So whatever one makes more sense to you, go with that in your notes. You always have your notes and you have to do this for me, so don't worry about it, memorizing it. Okay, so try it for yourself. Here's your points. I put them in order for you, calculate the standard deviation. Pause the video and give it a go. Okay, did you get 5.09? If you did not, double check your decimal place. Make sure you have at least 2 decimal points. Otherwise, when you have that many decimal points, it can definitely mess up your numbers. And then I want you to figure out the standard deviation for hand length. Okay, and I will be checking your data, so make sure you put that in your notes as well. Okay, so how do we work with this? So here's another IB question. So we have 2 different populations of sparrows are shown in the table below. So you have 2 populations, population 1, population 2. Here's the mass of the birds. First one is calculate the mean for mass of birds of population 1. This is an actual IB exam question, 1 point. So actually calculate it, pause the video, what are you going to get? Hopefully you get 24.64 grams. And then with reference to the data shown, but not actually calculating it, what is meant by the term standard deviation? So standard deviation would be how far that the values are from the mean. So the larger the standard deviation, the more variation there is, the bigger range in the data set. Okay, let's talk about error bars. So once we have the standard deviation calculated, we can use error bars to help us. A lot of IB exam questions have error bars in them, and you should definitely use them in your IA. So when we create a graph, if you're plotting the mean, not just that one, but it has to be the mean you're plotting, then we often include error bars because that's showing how far that mean, how much variation is in that mean. So usually the standard is to say that an error bar is 1 standard deviation. If they don't tell you how much it is, you can assume it's 1, but you should definitely always say as part of your graph title, if this error bar is 1 standard deviation from the mean, and that way people know what it means. Okay, so why would that be useful? Why would it be useful to have error bars? Well, it tells you just how much variation there is in that. If you just look at the mean and you don't have any idea of how much variation is, it's not very helpful for knowing how close your data points are, how reliable your data set is, that kind of thing. So you look here, my bar number 4 has a very small error bar, just a little bit above, a little bit below, so not too big variation in this group, group 4. So my standard deviation is 1.75. But in this one, look how big that error bar is, group 1. 3.84 standard deviations are really big. So that means within 68% of the data is 3.84 points above and below the mean of 14.23. Now, if I just left it just with the bar graph and none of these error bars, I would think that I wouldn't know how much variation there is in this data. Like number 3 has a pretty big standard deviation as well, 3.59. So error bars really help us understand how much error or how much likelihood there is for error in a data set. A big error bar should be flashing red lights in your mind. Something's up with this data. It does not seem to be very reliable. There's something going on. There's a lot of variation in the data here. Okay, now when error bars overlap, that's a really good hint about the significance of that data. So if they do overlap, it means any difference between them is probably not significant. And that's because data points within one single standard deviation on both sides are equal. So here and here, because these different treatments in the experiment, they've had the same data points because there's overlap in a single standard deviation. Here there's less overlap, it's more likely to be significant, but it's not guaranteed. And here there's no overlap, it's a much bigger chance these are going to be significant. Even though there's a big error bar here, there's still no overlap between this error bar and that one. Okay, so if they do not overlap, like in this case, most likely the data is significant. The difference is caused by something besides a random chance. But you can't be sure until you do a statistical test. We're going to start next class learning about the t-test and Pearson's correlation. And that's a simple test you can use depending on what your data set is. Okay, so here we have some graph with some really scary giant error bars. So under IB exam question, so a study was carried out to monitor mortality rates resulting from coronary heart disease in people with and without diabetes. The data show the coronary heart disease mortality rates for 2 time periods. So we have 87-96 and 03 to 09. Look how giant these error bars are. That's crazy. Okay, this one's nice and small though. So with no diabetes, it's much smaller. There's definitely a significant difference. So we're most likely to see a difference here between these two because there's no overlap between the error bars. That not having diabetes and having diabetes is very different for mortality rate. Those who do have diabetes are much more likely to die from coronary heart disease than those who don't. Whereas now, the second time period, they're very similar levels. So must be some other variables happening here. I should talk about both those things. Compare and contrast always means things are the same and things are different. Okay, so you notice here that no diabetes actually is higher than without diabetes, so no diabetes here at the different time periods. And you also should notice here that we have much bigger error for both cases in both people who have diabetes than there is in case of people who don't have diabetes. Both times the error bars here are much bigger than the error bars here. Those are things you can say to your points. Okay, so here's another one. Here is a line graph that has error bars. So the error bars can only show up on points that are a mean value, right? So here we have catalase activity in bacteria in extreme environments. And they use a strain of vector that says high catalase activity. So here's the concentration in millimolar of hydrogen peroxide, and here's a catalase activity. You notice how not all the data points have error bars, means not all of them are means. So these ones, you can talk about the relationship between increasing hydrogen peroxide concentration and catalase activity. So as hydrogen peroxide concentration increases, so does catalase activity up to about 70 millimolar, and then after that there's a decrease further. And with the fact that there's a higher standard deviation here among those upper points. There's more variation over here than there is this last data point, and over here, much smaller standard deviation. Okay, here's another set of graphs with error bars. So we have cells that are going to become neurons, differentiate in the neural tube. They grow and mature under the influence of chemical and other signals. And the influence of insulin like growth factor was investigated using in vitro olfactory sensory neurons. The turning angle and extension of growth of these neurons was measured. So we have a turning angle of those with insulin-like growth factor and the control, and then we have the neuron extension of insulin growth factor and control. The question is, evaluate the claim that insulin growth factor influences turning angle and neuron extension. Well, you can definitely say it definitely influences turning angle. Look how big this bar is. The mean is very high, and the control is at 0. No turning angle at all. No overlap in error bars. This is definitely significant for turning angle. But if I look here, there's similar, and I can see my error bars, they do overlap, so as there's no significant thing here with neural extension being affected by IGF. So you need to understand what IGF is or anything to do this. You have to understand how to read the graphs, how the error bars tell you. Okay, that's the end of today's lesson. So where you should be at with your mock IA right now is to make sure you already should have chosen your IA topic and sent it to me. If I haven't received it by Monday, what is the date tomorrow? Monday the 11th. Then you need to get onto it. Okay, guys, I'm going to start making a list, keeping track of who's at what stage with this. If you've done that, and once your topic has been approved, so you already have topics approved, which is great, then you're going to write your question, hypothesis, variables, constants, your control, experimental group, if that's applicable for your experiment, what your methodology is, what your procedure first draft, all that kind of stuff. And I'm going to ask you to send it to me at least one time to double check it. I don't want you to make an error in your procedure or your setup and then spend hours collecting data and then realize that you could have changed it significantly and did a much better job. So please communicate with me regularly through email, and that will make sure we're all on the same track and you do a really good job with your mock IA, so you can do an even better job with your real IA next fall and get a really good grade for that 20% of your IB score. Remember, this is your summative for this unit, your last summative to really kind of boost your second semester grade. Okay, so your homework is keep working on the planning component of your investigation, upload the notes, of course, from today's lesson, and working towards your complete IA, which is due on May 27th. All right, guys, everyone's staying home and staying safe, and you had a good weekend. Take care.